Hi, this is ADEEL KHAN from Academia Sinica. My research is inspired by mirror symmetry. Mirror symmetry was discovered by string theorists in the late 80s. It predicts a duality between Calabi-Yau manifolds, where the role of the complex structure on one manifold is exchanged with the role of the symplectic structure on the dual manifold, which is the so-called mirror. This is a surprisingly powerful phenomenon. In 1991, a team of string theorists shocked mathematicians by using mirror symmetry to solve an open problem in enumerative geometry. Namely, they were able to compute the number of rational curves on Calabi-Yau manifolds. Eventually, mathematicians tried to understand these calculations from the mathematical perspective, and this led to several new mathematical theories. The first one is Chromosome theory. Kontsevich introduced the Chromosome invariance using key new concepts he introduced, namely stable maps and virtual fundamental classes, in order to give a mathematical framework for this enumeration of curves problem. The second new theory introduced by Kontsevich also around 1994 is the homological mirror symmetry conjecture. So this uses the language of category theory. On one side, we can take a complex algebraic variety and look at the category or the derived category of coherent sheaves. On the other side, we can take a symplectic manifold, which would be the mirror, and we can take a certain category built out of Lagrangians on that manifold. So this is an idea due to Fukaya. He came up with this idea around 1993, and Kontsevich realized that very natural formulation of mirror symmetry is that there should be an equivalence between these two categories. These are still very active areas of research today, but there are certain foundational difficulties I want to talk about. Basically, these boil down to non-transversality phenomena. So let me give you a very basic example of this. Suppose we have two smooth algebraic curves in the complex projective plane, say of degrees m and n. Generically, we know that they would intersect in exactly m times n points by Bézout's theorem. However, non-generically, the intersection can degenerate poorly. So it could become non-proper, or it can become non-transverse. So for example, in this picture, we have an example where we have a degree 2 curve and a degree 1 curve, and we degenerate the line into a non-transverse situation. So we start with 2 intersection points, and we end up with only 1 intersection point, just by deforming the line a little bit. So this is a very basic example of non-transversality. So one way to deal with this phenomenon is based on a theory of derived algebraic geometry introduced by Toen and Wissossi and Jacob Lurie around 2004. The idea of this comes from Serre's intersection formula, which says that in the case of proper intersections, we can compute the multiplicity using the derived tensor product, which is some kind of homological algebra gadget, which we can think of as a homological perturbation of the intersection. The point is that in derived algebraic geometry, that derived tensor product actually appears very naturally as the coordinate ring of the derived intersection. So using this derived intersection, we can always, if we replace the classical intersection by the derived intersection, we can always compute the correct multiplicity, even in the non-transverse case. That's the idea. So what does this have to do with Chromosome theory and homological mirror symmetry? Well, the point is that both of these theories rely crucially on Kontsevich's moduli space of stable maps into a smooth projective variety or a symplectic manifold. We might call it pseudo-holomorphic curves in that case. But either way, we have this moduli space that we have to deal with. And in order to define these Chromosome invariants or to define the Fukaya category, we have to do some kind of integration over a fundamental class of the space. The problem is the space looks very bad from the perspective of classical algebraic geometry because it is cut out in a non-transverse way in some ambient space. So from the perspective of derived algebraic geometry, we should take the derived intersection instead, and we get this kind of derived moduli space. Turns out that anytime you have this kind of moduli space given in this way, so-called quasi-smooth space, you can always define very naturally a virtual fundamental class in the sense of Kontsevich and define these invariants. In some ongoing projects I'm working on, I'm trying to define an analog of this in the language of derived differential geometry to deal with the case when X is a symplectic manifold, as well as an analog in non-Archimedean geometry, inspired by a recent non-Archimedean perspective proposed by Concevic and Sobolov. Another project is trying to do a kind of derived version of Lagrangian floor theory to give a new rigorous definition of the Kokai category.